Thank you. It's a great honor and a pleasure to be here. And I apologize that I'm so behind in this field. I worked on it for about 2 or 3 years, from 1990 to 1992, a little bit before. And much of what I did had to do with secondary nucleation. And since then I have worked on other things, so I'm embarrassed that much of what you tell me is new to me when I should, or it's been since 3 weeks when I was asked to write this thing, or maybe 4. So anyhow, the main thing I think that you'll be interested in, and maybe it's not new to you, is a mechanism for deracemization by crystal grinding. But I thought I could tell you a little bit about the other stuff we did that's, I think, relevant in a way first. So I've been working, I was up till 6 o'clock this morning trying to convert all my old overheads into PowerPoint so I could show you. And I didn't quite make it. And then when I did it, I find out I have way too much stuff anyhow. So I'll just show you what I would have told you. Okay, and then I'll go on. The main time I want to spend on this, because I think it's what you'll be most interested in, and what I'm especially interested in getting your comments on. Now, getting something homochiral is a question of correlation, getting things to correlate with one another. But I made this, 17 or 18 years ago, in the context of secondary nucleation. And there are different types of correlation within sets of crystals. There are sources for that type of correlation, and then and tests that you can use to see whether it applies. There's simple numerical, that if you have secondary nucleation, you tend to get the same hand. And you can test it by measuring the enantiomeric excess of crystals, for example, in sodium chlorate, but always compare it to what you expect for the standard deviation to see whether it's significant. Then there can be temporal correlation. You take a flask, you do the crystallization, heat it to dissolve it again, do the crystallization again, do it again, do it again. See whether there's random right and left-handed in that. So if there were persistent embryos that you never destroy, even by heating a great deal, then it's conceivable you'll come back. So you can test that by sequence statistics to see whether the sequence right, left is random or deterministic. And finally, there's spatial correlation. That if you do not stir, right, it's still possible that pieces break off, tiny pieces, and float away. And in that case, if you have fracture or budding from the crystals, then you can get spatial correlation. One hand tends to be in one region and another hand in the other region. Sometimes that could be very obvious, but sometimes it's not so obvious, and you have to have some way of measuring it to see whether it's random or not. And we used fractal dimension to analyze that situation. So there's too much to tell you about our work on this, but I'll just show you a little bit about it. First, a little bit about numerical correlation of sodium chlorate, where you just count the 2 enantiomers. When you crystallize with stirring, and of course you know, and Mayer reminded you about Dilip Kondapudi doing this in 1990. And Randy Carter in our research group was the one who did this repetition, and I'll just show it to you so maybe you've seen it. But so we have a concentrated solution of supersaturated solution of sodium chlorate, and it's stirring with a magnetic stirrer, a centimeter. And it's been stirring for an hour, nothing happening, just stir, 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 no point to show you that. But I'm going to show you what happened during this 15-minute period. Okay? So during the first 7 minutes, it stir, 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 nothing happens. Okay? But at the end of that 15 minutes, something is beginning to happen. And you can see there, a crystal has formed down here someplace out of the view, and it's growing slowly up in that direction. So you see the corner of the crystal. So we stir, stir, stir for another 7 minutes. And now the crystal has grown to get very near the stirrer. And in fact, it's so near the stirrer that at this time, this is in 1990, 31 minutes and 11 seconds, right? So this is an hour after, or an hour and 14 minutes after stirring. At that point, when the crystal is out to there, the crystal actually, the stirrer strikes the crystal, and you can see in the video that the magnet, which has been spinning steadily, makes a little move. Okay, so that's at this point right here, 14 of the 15 minutes. Okay, and it's 11 seconds there. So the next frame, still stirring, is 9 seconds later. So that's here. 9 seconds after the first collision. And then this is 15 seconds after the first collision. And there have been 32 collisions in this 15 seconds. But notice that the corner is still sharp. That's related to how does different kinds of crushing do different things. But this one doesn't knock anything off that you can see at this magnification. I mean, nothing of a millimeter dimension, certainly. Okay. And then the stirrer, having struck it, when you do magnetic stirring, sometimes it stops. And it stopped. It went over here, and I turned the stirrer off. Okay. But notice that it's becoming grainy, the background. And here it is 30 seconds later, or 15 seconds, whatever it is, a certain number of seconds later, and it's getting much more grainy. And if then we look at it for another, whatever, minute, and blow it up times 7, you see their crystals full, and they're all the same left hand as the original crystal. So I think there's no chance, you've been stirring for an hour and 15 minutes, that everything happened within 15 seconds, to me, means that the collision is what started all these crystals growing. So secondary nucleation. Now, so I wrote this or Randy and I wrote it in On Go to Camille, and only many years later did I look on my bookshelf at this book, which I had bought when I was a student. Here's the title page, and you can see what it says, that it was written in 1960. That's when I bought it, a paperback, that for secondary school students and their teachers. And it's a nice book, and it has an appendices at the end, which are recommended science projects for students in secondary schools. So, for example, experiment number 6 here is to use a piece of sodium nitrate, which is both glided and unglided parts, as a seed from which to grow a larger twinned crystal. So grow a big twinned crystal, that could be a project. But project number 7 is particularly relevant. The randomness with which right-handed and left-handed seeds of sodium chlorate form in a solution might be upset by suitable influences. So this is going to be a project to test how you could change that. And it says, for example, if seeds formed in some solvent which itself was right or left-handed, a chiral solvent, like citronella, this upset might occur. So you could do that for a science project. But there's a caution at the end of this paragraph, which you see right here. It says, you must be careful that the seeds you finally examined are not all formed from a single seed which has been knocked about in the solution, producing more of its own type. There's not a lot new under the sun. Okay, and in fact, it's much older than that. Marbach, in 1856, with sodium chlorate, said every time the experiment was repeated, the weights of right and left sodium chlorate crystals were uneven. You don't get 50-50. And Landolt in 1896, whether the precipitates contain predominantly R or L, no doubt depends on the rotation sense of the first tiny crystal formed in the precipitation. Or Akel in Munich in 1896. There were, among 40 or more crystals that were investigated, the relationship of left to right was 4-to-1. So if you have a ratio of 4-to-1, that would be 32-to-8 out of 40. And that's an enantiomeric excess of 3.8 sigma. So that's never going to happen by chance, or not very often, unless Akel was really, really lucky. Okay, so same thing. Or Virubov, which we just heard quoted from Professor Rebo. Tous les cristaux sans exception sont dextrogires. All the crystals are right-handed of the silicotungstate. Or Charles Sauret in Geneva is a particularly poignant character. He was a professor of physics. His father, Jean-Louis Sauret, was the man of the Sauret bands in spectroscopy. Sauret was the only person who passed the mathematics examination in Paris in the year when he was a student, except one other, Poincaré. Okay, but anyhow, in 1898, he was working on this subject, which was a very popular subject at the time. So he did this carbonate, and he found 221 right-handed, 165 left. That's 2.9 sigma. He didn't use sigmas, but you can see that it's quite significant. Or Virubov silica tungstate, 86 to 0, right? He said there was no effect from magnetic field or from impurities. He used sealed tubes for that one. Here there was no effect from magnetic field or impurities, and he used sealed tubes. Then he did sodium chlorate, 4,657 to 6,504, which is 17.5 sigma, right, away from random. No effect from magnetic, from quartz. No effect from tartrate. No effect from stirring. That's interesting, isn't it? He did that over a 4-year period, while he was also the rector of the institute. And then he did sodium chloride again in 50 sealed tubes, 433 to 411, only 0.8 sigma. Each was recrystallized 19 times successively, right? Among all those examples, there were 413 retention from one to the next, 333 inversion. That's 2.9 sigmas for the temporal correlation. Okay, he described this to the Academy in Geneva, which was reported in the Proceedings of the Academy by Villiers in 1898. He said, Professor Sauret has made long research to study the causes that give rise to the production of left or right crystals in active salts that are active in the crystal state and inactive in solution. Although the author hasn't been able to obtain any positive results, that's after all that, thousands and thousands, he hasn't obtained any positive results, still his work is important for the statistical results that it contains. So poor Sauret, he himself said in 1899, all of these results are very uncertain and suggest no explanation. It would be desirable to undertake research on this subject from several sides to furnish a sufficient number of facts to be conclusive. So doing 15,000 crystals is not enough to be sufficient. So poor Sauret, during the 3 years that followed, Sauret, worn out and sick, abandoned for the time his scientific work. So you are warned. It's dangerous to work on these problems. He died in 1904. That's from his obituary. Okay, but William Jackson Pope was made of sterner stuff. In fact, he did a lot, Kipping and Pope, presumably. And he, in his obituary, Kipping wrote, I think the happiest hours of his life were those spent in the dark room with his goniometer, in calculating the results of his measurement and in drawing the crystal figures. He seemed never to tire of this work, and his desire for new compounds to measure was almost insatiable. So here was a man and a problem that were made for one another. Now, I could tell you a lot about this, but I won't. I'll show you the slides just quickly. So we are here. And this is all about analyzing Kipping and Pope's work and showing that there actually it's not random at all. It's very non-random what they found. Although most people say it's random. It absolutely isn't. And in a way, I think they cheated to make it because they thought it should be random. But I have other things I want to tell you, so I'm not going to tell you that. I'll tell you privately if you want to hear. And then the next thing I would have talked about is spatial correlation. If you don't stir the dishes of sodium chlorate and just let the crystals grow and look at the distribution of right and left hand, can you use that to see whether there's secondary nucleation? And you can, analyzing it by fractal dimension. And then we wondered if this happens with sodium chlorate, what about quartz? Let me show you, I'll just show you these few slides here. So is there numerical or spatial correlation in quartz crystals? Because quartz, as you know, is of this kind. It's right and left-handed. So Fred Howard was a student who worked on that. That's James Dwight Dana, who was a professor at Yale, as you see, in the 19th century of geology. You know Dana mineralogy?
Yes.
Everybody knows it, because this book is still in print. This was in 1960, and it was in the 17th edition and the 7th edition of different parts of his book. It's the Bible of field geology. Yes? And this particular volume, edited by Clifford Frondell at Harvard, this was 1962, is about the silicate minerals, and in particular about quartz. It's the Bible of quartz. And in it, he has a table of the relative frequency of right and left quartz. You notice that 16,807 quartz crystals from nature had been characterized as to whether they were right or left as of that time. And it was found that in every case, more left than right, average 50.5%, and the percent right, 49.5. So, clearly, with the sample so big, there must be significance to that. At least that's what, but notice this, that footnote there on the sample from Russia. It said this figure was obtained after throwing out 931 crystals from the original sample, because they came from localities which had proportions differing by more than 5% from the average of the other work. So it looked like there was something funny going on with these 931, so they were not included in the table. Right? If these data are included, the proportion of left crystals is 51.1% instead of 50.5. Much, much more significant. Okay? And then a man named Mason, you may know him, he's at FRS in England, on the basis of this wrote many papers in this period, published in good places, where he says minus quartz crystals are more abundant with an enantiomeric excess of 1.4%. Notice, to get that number, he put those crystals back in that Frondell threw out. Okay, over a set of samples totaling 17,738. A chance origin of this excess has only a 2.8% probability, QED. So he wants the electroweak force to break the symmetry. Okay. But by the time Mason published this, Frondell had published another paper, and he had found even more quartz crystals. Right? So at this page in 1978, he had 26,000 instead of 18,000. 26,000 macroscopic crystals, 13,000 right, 12,974 were left-handed, and you notice that this is more right than left. So it turned around. So do statistics lie? Or might it be that these crystals were not independent of one another? Because the crystals from a particular locality might be related to one another. There might be a correlation. And then the sample is not nearly as big as 17,000. It's only how many different sites you had, which you can count on two hands of fingers, right? So we did actual work on that. We went and, well, I'll show you just one. Let me go quickly here and not show you. So this is how to tell which hand quartz is. That's actually not a good way. You have to look at twinning. And this particular crystal, which we etched and looked at, is just twinned in all sorts of different ways. Most quartz crystals are not uniformly of one hand. Some are. So we found So there's a quartz crystal from the Rio Doce, and this is stuff about where those crystals came from. And this is Fred Howard, who worked in our research group, and he was a football player. And here you can see him stopping a run by the Princeton runner. And the next day after that game, this is us at the Crystal Grove campsite and diamond mine in New York, right? And what we did was break up rocks, big rocks. Here's a pick. This is a big pick, you know, like that. And the dolomite we broke up, and we found in it pockets which had quartz crystals, and even better were pockets that had many, many small quartz crystals for purposes of statistics. So there are right-handed crystals from one hole, and then what we had to do was open new holes. So we got them all from one hole, and things like that. And we had to then put each of these crystals into hydrofluoric acid to etch them, study them under a microscope to see what hand they were. And so there were, in all, we did 609 of those little crystals, right? 312 right, 297 left. It's only 0.6 sigmas, so 50-50. Okay, but this is it, hole by hole, right? And notice that here's 3 sigma away from 50-50. That's really big, right? So from one hole to another, there's not correlation, but within holes, there's a correlation. So I think that that's what the quartz story is. But I don't want to spend more time on that now. Let's see. Oh, well, I can show you this slide here. Sorry. This is what you expect for a certain number of sigmas, the gray. And this is what we actually observed. Right? Much more than random. There are very few that are relatively few close to 50-50, and many that are much too big. So clearly there's correlation within a given hole in the rock. Okay. Now let's see where we are. I think I'm just about ready to go on to the other topic. Yeah, okay, so now we're ready for the main talk. Oops. And I presented a preview of this on Friday, so those of you who were here then, I apologize for dragging you through this again. So deracemization of sodium chlorate with grinding, it's a substance which is achiral in solution, and then we'll talk about Vim's work with something that's chiral in solution, and it's of course due to Edma in 2005. And this is Vim's work that he just told you about. So those things, as you can see, are chiral because he mentioned those hydrogen, which is in or out of the board, or if you rotate it 180 degrees to show that it's a mirror, they're both back in, but anyhow, one's right-handed, one's left-handed, and they can be interconverted in solution, but presumably not in the solid. Do you think it doesn't do it in the solid? Okay, so only in solution with that base are you able to go back and forth. Okay, now here's the plot which he showed you, and remember you start with very small enantiomeric excess in favor of either the R or the S, and in time it evolves in this to 100% enantiomer excess, and it has a curious shape which is acceleratory, so it's autocatalytic. It can't. It's just like what Gedma found in the case of sodium chlorate, that it's autocatalytic. So it's not a normal chemical reaction which slows down as you near equilibrium. Okay, so that's remarkable. So I got a question from an editor of Nature. He asked me 2 questions. Do you find these observations convincing? And will I make you unhappy if I say at the beginning I found your results very surprising, your original results? You found them surprising too. Okay, good. I'm in good company. Okay. But I look and I did various kinds of analysis of Vim's results, and he told you about it. They look very good. Yes, I think that's fine. And you think this paper is worth reporting in News and Views? And I said that I think it's really valuable but how am I going to write this if I don't have any idea how it works? So this was 4 weeks ago now, I think, so I started reading papers that you people, some of you have been writing, which I am embarrassed to say that I hadn't been reading since 1992. Now, how could it happen? I had one idea that is wrong. Mayor and I have granddaughters, no grandsons. So our name, our last name, if history is a guide, will die out, right? But the same thing could happen with crystals. Crystals have progeny, and the progeny of a particular crystal could happen to die out. Now, you know about mitochondrial Eve, that all our mitochondria come from one individual about 80,000 years ago because all the other strains died out. Could it be that way with crystals? How many generations do you have to go through? If you have a constant number of crystals, so they're always dissolving in steady state, how long would, ultimately it has to be that in the fullness of time, even though there are many crystals, all strains must die out except one. And the only question is, how long does that take? And what form does it use to approach that? Okay. So I had worked with a statistician, and he showed that this is the way it should approach equilibrium for the mitochondrial Eve. Approach, not equilibrium, approach 100%, right? So you see, first, that it's not autocatalytic. It slows down the way you expect things to do normally. And it's not deterministic, because which crystal ends up is not, it's not the one that's in majority, it's only be in proportion. If there are 60 of one and 40 of the other, one will have a 60%, one hand has a 60% chance, the other 40. It's not all going to go to something that's in tiny excess. So forget mitochondrial Eve. But during this time, I was also, while I was thinking about this, I was also reading papers, and I was particularly struck, well, and I started emailing Elias, and indirectly then Vim, to ask if they understood how this worked. And they were very kindly sent their preprint, which has been accepted, going to be published soon, I think, about Ostwald ripening, the stuff that Vim told you about. But when I read it, this prompted two thoughts. And the first thought was that somehow you must consider solution to understand the drive from minor to major. It's funny, right? Usually spontaneous things go from a major to a minor to approach equilibrium. This goes from the small to the large. That's backwards usually. And it's happening in solution. So there's something must be going on in solution, which is not directly playing a role in the calculation. Although the way the calculation is done is meant to mimic what might happen in solution, but treating it as pairs of solids. Is that fair to say?
Yeah, what we do is we only look at the communication or the transport of material between the solids.
Right. So there's no step in your program that's dissolution, and no step that's growth. It's transfer from one crystal to another, which is intended to mimic what would happen in solution. For example, the slow interconversion in solution is mimicked by homochiral being faster than heterochiral, that kind of thing. But anyhow, it occurred to me that maybe one needs to consider, or could at least consider, the solution. And the second thought was that the algorithm succeeds. The reason it succeeds is that it retards minor to major transfer. That's what you put in, and that's what does it, yes? Okay. During heterochiral crystal collisions. So there's no explicit growth or dissolution. And it works very well. So again, while I was reading this, I looked at other papers and was particularly struck by the paper of Makio Waha in Nagoya in 2004. He actually published the paper before you published the experimental paper. I don't know how you told him about it.
Yeah, I sent my paper.
You sent your paper to him? And much of the same idea was implemented by Saito, or very related approach in the next year. And this is that paper by Waha. And the crucial, from my point of view, the crucial few sentences is that there's a minimum size cluster that possesses chirality. That is, a monomer doesn't possess chirality. A dimer probably isn't chiral, or at least it's not stable in its chirality. But there's some size cluster that will persist in its chirality for a relevant time period. Right? And the growth of chiral crystals proceeds via incorporation of the chiral units. So these chiral clusters can go intact into an existing crystal. Okay? So those are the two, and incidentally, the reason you say it's chiral is so that it can discriminate between the right and left-handed crystals, that it will go faster into the same crystal than into the other crystal. It may go both, but it must be faster one way than the other. And the reason it should be a cluster and not another crystal is it must be that if it's not incorporated, it dissolves. It's subcritical. So subcritical, chiral, and ablated, knocked off, right? That's so that that step will not be reversible. Okay, so this is Waha's model, and we'll just go through it. That's a picture of his paper, the page, and we'll just go through and show what's in it. Okay, first, this is the differential equation, the change in time of the crystalline material, the big crystals that grow because the solution is super saturated with respect to these crystals, these big crystals. And so how do they, and then there's also, and notice incidentally that this ignores particle discreteness. The only thing it talks about is how many molecules are in that population, not how many are in a given particle. The only thing that you know about the particle is it's supercritical, so that it will grow and not dissolve. Or anyhow, you can neglect the possibility of its dissolving, that is going away, becoming smaller. Okay. So there's nothing about size distribution, nothing about ripening, except for the fact that subcritical tiny ones must dissolve unless they're saved by incorporating into another one, and the big ones grow. That's the only written connection with Ostwald ripening. Okay, so then there's the cluster material, the things that are subcritical, that are destined to dissolve. And there's the dissolved material. So there's 5 species: right-handed big crystals, right-handed little crystals, or clusters, left-handed big crystals, left-handed clusters, and molecules in solution. And now, what are the steps? First, the crystals, the big crystals, can grow. And the growth is proportional to how many crystals there are on which to add, and to how much material is in solution. I think that's reasonably second order. And at the same time, of course, if they deposit, they come out of the solution. The second step is growth by cluster absorption. Remember, we said that an intact chiral cluster can be absorbed on a big crystal. Okay, so that's second order in the cluster and the crystal. Has a certain rate constant. And of course, when it does, that means you lose material from clusters when you add it to a big crystal from the population of clusters. Okay? And then there's growth by dimerization of clusters. The clusters are subcritical, but maybe if 2 of them come together, the particle becomes supercritical. So this is nucleation by the aggregation of subcritical clusters. And of course, when that happens, when the clusters do this, they come away from being clusters. And then there's loss to dissolution, right? So the crystals can dissolve, and when they dissolve, they increase the number in solution. And they can be lost by breaking off the ablation, right? So you lose proportional to how many crystals you have, right? And those become small, join the population of clusters, that material, okay? Now there are things that don't involve the crystal. There's primary nucleation, which comes from two of these coming together, right? Which is higher order, maybe two, but it could be any order in the amount of material in solution to make the clusters. And there's cluster dissolution, because if a subcritical thing is not saved by going on another crystal, it dissolves, right? And that will increase the material in solution. So those are the differential equations whose solution is sought. But you'll notice that some of these probably are not relevant in the system we're talking about, because there are so many crystals there and clusters. It's very unlikely that the formation of a new cluster makes any difference. And it's very unlikely that this is important, making clusters coming together to make a new crystal. It could be added, but if it were added, it would be in the same direction. But it's easier to ignore it, because I can't believe that that's the main thing that's going on in this case. You could put it in, I don't think it would change anything. Okay, so to simplify things and try to see how it might work, let's take those steps out. Now, most of all, I said to my the theorist who I'm working with, I don't think it has anything fundamentally to do with Ostwald ripening. Not that Ostwald ripening couldn't occur, and maybe, and we've heard a way it might occur and it might play a role, but it seems to me that this mechanism that we're talking about here doesn't need Ostwald ripening. And in fact, exactly how the crystals behave, I don't know. That's why I was asking Wim, because I can imagine that with a certain kind of grinding over a period of many, many weeks, you must reach a stationary state where crystals are being ground down as much as they're being deposited. So you have to reach some steady distribution in size, I believe. Okay, so the only connection with Ostwald ripening theory is that big crystals grow and small crystals dissolve. That's a feature of both these. And each of these in this theory has a fixed rate constant. In truth, there will be little differences in the effective rate constant, and certainly when you're very near the critical size, right? And Wim takes care of that explicitly by this 1 over the cube root of the radius. Or whatever power it is, I forget which power. But anyhow, you take the size and the differences in rates explicitly into account. But this, I don't think you need to. I think all you do is have the big ones grow, the small ones go away, unless they're saved by growing with another crystal. Okay? So now I'll show you a steady state visualization of why the system could drive to chiral purity if you're constantly abrading pieces from the big crystal. Okay, so for this purpose, to make it as simple as possible, let's just suppose there's one crystal of one hand and two crystals of the other hand. That's more of one than the other. Okay? And they're exactly the same size and shape. Because in this steady state population, you must be able to say, here's this one, here's this one, here's this one, here's this one. So it must be possible to compare things of the same size and shape. And there could be different sizes and shapes, and in truth, they would have slightly different rates. But I don't think that's a key feature of this. So we assume they're the same size. Now first let's look at static dissolution. Molecules come off the crystals, and they go back onto the crystals from the pool in solution. But notice that the arrows are exactly the same for this crystal as they are for this crystal with an achiral solution. This is exactly the same as this. This is exactly the same as this. And the same would be true for this crystal. So they're the same rates for every crystal, on and off. Right? So that implies that the ratio must be stable. You can't go one way or the other for that. Okay, now let's consider that you're knocking pieces off. So ablation of subcritical fragments. So each crystal gets pieces knocked off, and these crystals are subcritical, so they must dissolve. When they dissolve, they increase the concentration in solution, which increases the flow back on. And in steady state, that balances. The increased dissolution is balanced by increased deposition. Right? And again, all the arrows are the same. Right? Same rate for every crystal, whether it's green or red. Right? So this ratio will be stable. Okay. Now, add the special thing, which is that subcritical fragments can be reincorporated. Right? Now, the effect of that is to lower the flow through dissolution, because this crystal, which is made at a given rate, either dissolves or is reincorporated. If it's allowed to reincorporate, that reduces the amount of material that goes here. It reduces the concentration here. It reduces the flow back. But again, everything is the same between the two crystals, except that the green ones can deposit on two crystals and this on only one, if it's absolutely selective. That's what Waha's theory means when it says that the crystal is that the clusters are chiral, that they can discriminate between the two. Now, maybe the discrimination isn't perfect. Maybe they're only 1% better at going on one than going on the mirror image. But still, they're not exactly the same, and Bim, I think, agrees with that kind of thing. Okay, so let's suppose so this is only true if the incorporation is selected. If you have these, this one could go on two, these could each go on another one. Here, but if you assume that this is bigger than this, right, if each crystal is selective, right, chiral subcritical clusters, then it will be true, if incorporation is selective, then the slowing down is more slowing down, slower dissolution for the majority crystals. This is really the key feature. So I'll pause just a minute if you want to convince yourself that that must be true. If more of these can be reincorporated because of the cross, the green ones, but not available here, then the reincorporation of subcritical fragments slows this forced dissolution. This is a force because it only happens because you're knocking off small pieces. And you'll slow that down more for the green than for the red. So now this dissolution is faster than either of these. Not faster than their sum, but faster than either one. Okay? The green crystals dissolve more slowly than the red ones if you include that they could be reincorporated selectively.
The question is, you're assuming that you have the chiral clusters.
Yeah.
But we know that sodium chloride and other molecules are solvated in solution.
Yeah.
It may well be that the population of these clusters in solution is known, that the number of the achiral one is quite substantial, and only when they're striking the surface they become chiral.
That's true, but if that's in that case, these arrows, the dashed ones, are the same as the non-dashed ones. It doesn't make any difference whether you started here or here in your rate of incorporating here. And if that's true, this mechanism doesn't work because it depends on the incorporation being selective, and that's what Waha meant when he said chiral clusters. And it may be that 99.9% of the clusters that reincorporate are not selective.
No, there may be.
But if there's any bias, this can happen. Then, of course, you have to worry about the balance of rates. How big is the difference? How fast are you ablating, and so on. But if there's in principle, these are less, each one of these is smaller than this. Because if incorporation is selective, homochiral incorporation easier than heterochiral. It doesn't mean the other one can't happen, but one should be easier. Okay, so this is why Waha's subcritical clusters must be chiral, so that there can be a selective incorporation.
So another question, Mike. If you measure the rotation of the solution of this, let's say, because sodium chloride is achiral in solution.
Yeah.
According to what you're saying now, if you take excess of that, then you should find some optical activity in the solution.
Due to these little things.
Yeah.
But the little things are not very much. You're going to have to look carefully.
In principle.
In principle, there will be due to those. In principle. But you have to be sure when you're measuring it that there are none of the big crystals there. And these don't last very long.
Yeah,
so
you might have
it's not an easy experiment. Yeah, I want easy. You look hard. You had a question?
Yes, and one explanation. The incorporation of chiral cluster into solution. The apportation of the major enantiomer is no more than the other one?
It is more, yes.
And you don't
This
have
one,
this...
this one is more than this one.
But
and the reason is
at the beginning,
that when you break this off, it can do two things. It can dissolve, or, according to Waha, it can reincorporate. And if it reincorporates, it does not dissolve.
For you,
so that effectively reduces this rate, or the flow through that channel.
But for you, the kinetic of the solution is the same than the kinetic of crystal growth in your model.
Yes.
Yes, and this is not real.
No, but there's a difference.
The
difference is because of this. Because these are chiral. This is not chiral.
But
so this, pardon me just a second, this rate is exactly the same as that rate.
Not exactly. Because
why not?
Because in chemistry there is the reversibility, the principle of reversibility.
No, but this is achiral.
Yes, but in physics there is no reversibility. The dissolution is very quickly, it's very fast. Growth is very slow, very slow. You can dissolve one crystal in a few seconds.
Yeah.
You must 1 day or many hours to grow this crystal.
But if it's let me address that first, and then you can continue. Okay. In steady state, the rate off and the rate on are balanced. In steady state.
But the kinetic is the same.
And the reason is that this size of the concentration in solution adjusts to make this equal this. That's what a steady state is. If dissolution is faster than growth, this will build up until this becomes the same as that. Although with the ablation, you also have this channel. So in steady state, on has to be this plus this, but not this plus this, because you have this possibility.
Does not mean that the both processes are similar. Don't mean that, because the growth is slow than the dissolution. Then the dissolution
the rate constant
may
be slow,
but
the rate is the same.
When crystal grow, there is dissolution. If crystal don't grow, there is not dissolution. The dissolution depends on the crystal growth. But the dissolution is very quickly, it's very fast. Crystal growth is very slow.
The reason dissolution is very fast is because the solvent is undersaturated, so not much comes back on, right? But once you build up concentrations, if you have lots and lots of solvent, everything will dissolve rapidly and nothing will come back on. But if the solvent is limited, then at a certain point the number going off matches the number coming on. And that's what happens in steady state.
Crystal growth means that one chiral species go on the surface of the crystal, there is diffusion on the surface, they find the correct place, they put it. It's a very complex process. Dissolution is a very fast process. Crystal growth is very complex. And crystal growth from chiral crystal is more complex. Much more complex.
I think maybe to be sure that I get through this, I should do this and we should talk about this. Okay? Is that reasonable?
Another thing more. At the beginning, you have two crystals, major phase, that dissolve. And only one crystal that dissolve. What put more crystal into dissolution?
But there are always more. There are always more here.
Yes, there is
than
more.
there are here.
More.
It's second order.
Yes.
The amount of that.
And
It's higher order. That is what's non-linear.
Yes, I know that.
Yeah.
This morning we have discussed another thing. Well, how much site available there is in every crystal?
It's the same on every crystal.
You can say only one side, for instance, in every crystal. And why then the cluster or the main phase can choose one or another crystal? Only there is one place.
But if there were one growth site here, one growth
Yes.
site here, one growth site here.
Yes, one.
But look at this. It's more likely to add to green, where there are two sites, than to add to red, where there's only one site. But per crystal, this crystal is the same as this. They each have one site.
Yes.
So it makes, if you look at each crystal, compare this crystal with this crystal.
Cluster.
Compare this crystal with this crystal.
You say cluster can go to one crystal or another one. In the green.
The green
But
one
it's
can go
not
here
here.
or here.
There is only one place, and there is the cluster.
Oh, you mean that the shape has to match?
What?
Do you mean it has to go back to exactly the same place it left?
Yes.
Oh, I think we can neglect that.
No.
Right? And probably, just
only
saying, I think that's, but that, I understand, let me
The
address
challenge
that.
is the same.
Okay, let me address that. That's an obvious problem, that if you have a funny shape for the thing, and there was a shape that matched here, they would fit, but only one place in all the universe would it fit exactly.
No, crystal.
Right?
It's a model.
Yes,
It's a model.
but while it was off, molecules from solution have been adding on here. It's not the same shape anymore. So that's never going to happen. But all big crystals have some flat areas. So the cluster likely has a flat area. At least some of the clusters. Doesn't have to be all of them.
Yeah,
but some of them have a flat area that will match a flat area. I think that's the most likely way to merge, is flat area to flat area.
Mike, all these surfaces are hydrated. And we know from our studies on crystal growth that the rate determining step of all these crystal growths of the various phases is the solvation, the stripping of the water molecules.
But it has to be a little more subtle. Okay, I got it.
And now
It's a little more subtle though, because you say that the desolvation is the rate limiting step, but it can't be exactly. It doesn't go exactly, boom, and all the water goes out. It goes maybe like this, and a few waters come out, and a few waters come out, and then it goes like this, and a few more, and a few more, and a few more, and finally it settles down. And probably when it came initially, it has to turn to be just right. So at any place along that line, it might break apart. Maybe usually it goes together. But if one time in 100 it comes apart, that slows the process when it's wrong.
Yeah, but if I understand correctly your model, you're saying is the difference is in the red that is taking that one cluster of one endedness is striking one surface as compared to the red that the same cluster is going to strike the next one.
It'll strike at the same rate.
Okay, but they strike, but the reorganization. What I'm about to ask, what is the rate of the solvation, of the stripping of the solvent molecules from the surfaces of the crystal as compared to the rate of reorganization of one cluster into the other? If the rate of stripping of the solvent from the surface is much, much slower than as compared to the other, then you don't...
is that there is a little difference. It doesn't require that it absolutely is forbidden on one and easy on the other. All it requires, and that's what Waha means when he says it's chiral, that it's a little easier, at least a little easier on one than the other. Okay, now, let me go again. So in this case, the difference is that this is faster than either of these. So this one disproportionately feeds solution. But they come off from solution at the same rate. So that accomplishes a flow in this direction. So the minor goes to the major. And the only thing you need to assume is that incorporation is selective. A, that it occurs, and B, that it's selective. At least a little selective. And then you can argue about how selective it has to be.
I don't understand this.
And
only one thing. There is a cluster for every crystal.
yeah,
Why have advantage?
why have what?
Advantage.
Advantage?
Advantage, yes. I don't understand that.
I don't know what the advantage is.
Yes, there is one chiral crystal for
Yeah.
every crystal.
Yeah.
The green
What that
chiral
means,
crystal have
I'll let you go
advantage.
ahead, but what I mean by that is that the rate of coming off is the same for every crystal. There could be 2 from every, or 5 from every.
Cristobal,
But they're the same.
discussion after that. After that,
Yeah, well,
the discussion.
maybe I should finish.
I think that there are
Discuss.
probably many other discussions that we have because each one, most of the models here are so different from one another. And I think what we rather should
Yeah, we're just,
do
I think that's right. I think we better not have all the
is
discussion.
finish your lecture
Yeah,
and
thank
then
you.
after that we shall
Okay.
try to go.
Okay. Now, what happens if the pools are separate? Because the molecule in solution is chiral. So this is Vim's case, or your case of the amino acids. Okay, what if there's a barrier here? Then this machine operates, and this machine operates, but they're independent, right? But still, this is faster than this, for exactly the same reason I talked about before, right? The fact of there being a common pool did not affect that this was faster than this. That was only because of how many incorporation possibilities there are. Okay, but now, suppose that base catalysis drives the major toward the minor in solution. So there's more of this one in solution because it's dissolving faster, right? So it has to go on faster, and the only way it can go on faster is to have more stuff in solution. So there's more of this than there is of this in solution, because this is faster than this. Okay? Now, if you allow base catalysis in solution, the major, notice major toward minor in solution. This is major, and this is minor in the crystal. But in solution, this is major, and this is minor. Yeah, so that's happening now. And notice there's a population inversion between solution and solid. This is major in the solid. This is major in solution. And that's absolutely crucial. It's very, very important that that happen. Because if that doesn't happen, then you don't have this. If there's more of this than there is of this, the flow between these two manifolds will be in that direction. The flow is in this direction. So it must be, if that process happens in solution, that there's more of this than there is of this in solution. That's the only way. And that's testable in principle. Because you have more of one crystal than the other, you measure the concentration in solution, and it should invert in steady state. It may be a very small difference, so that might be hard. But in principle, it's possible. Maybe you could test it by your method, having a little bit more of one than the other. That can, what, you did?
Yeah.
But
But it's without rationalization,
pardon me?
one sheet back.
Yeah.
What I did is I started in the solution with, which is receiving, of course, and
But of what compound?
of my compound, the molecule.
Oh, without base,
Yes,
though.
without base.
Yeah.
So then you have a steady conglomerate. Yeah,
That's this.
And in the solid, we have 80% of the left-handed crystals and 20% of the right-handed crystals, maybe even more in a chimeric excess. And, well, we wait, we measure the enantiomeric excess of the solution, which is completely receiving, and of the solid, which is 80% or so. And then we start grinding for about a week or so.
Yeah, and pardon me, just let me interrupt there. Notice that this difference happens only when you're grinding, only because of this.
Yeah, this
so you start grinding.
Yeah, what I told you now is a zero experiment. So I just wanted to make sure that my solid composition was known. Then I started to grind, and I measured the solution concentration and also the solid enantiomeric excess. And I didn't see any differences. Also in the solution. That doesn't mean that this is not happening.
But it could be very, very small.
Yeah.
But otherwise, if this is the only connection between the right and the left, and isomerization happens only in solution, it must be that this is bigger than this. Maybe not measurable, but it must be bigger.
Yes, but I'm not sure if you need the clusters in this case.
If you need what?
What you showed, Cristobal,
Maybe we're getting into the discussion again.
Okay,
I think.
okay. Let us finish your lecture.
I'm almost
finish
done.
Your lecture and after that,
Be patient.
I'm going to have a long discussion.
Okay, so if we showed this, we showed this. I'm glad I didn't go into quartz. Okay, so again, faster dissolution of the minor population feeds the major population. So whether the molecules in solution be chiral or achiral, whether it's sodium chlorate or your amino acid derivative, retardation of dissolution by reincorporation of Iwaha's subcritical chiral abraded clusters drives the solid to chiral purity. Now notice, it's subcritical. That's so that they will dissolve if they don't do anything else. It's chiral. That means it's faster in reacting with the same solid than with the opposite solid. And it's abraded so that it can't go back on, except that is that the original abrasion is not reversible. Right? You can't just have, if you have normal breaking off of, just thermal breaking off of clusters, then detailed balance comes in and you must have the same flow in the opposite direction. So it has to be abraded. Note that nucleation doesn't enter this scheme. And that Ostwald ripening is not necessary here because we're assuming the same size all the time. Right? Nor, without selective reincorporation, is Ostwald ripening in itself sufficient to do this because it doesn't have that nonlinear feature to create a drive toward chiral purity in a polycrystalline sample. If you have a single crystal, then clearly it drives to that one crystal. But if it's polycrystalline, Ostwald ripening won't get you there. Or you could have, in principle, you could have selective nucleation, but I doubt that that's true. I mean, it's true, but I doubt that it's the source of the phenomenon. So I've been working on this with John Tully, who you can see from his blackboard is the theoretician. So he helped reformulate Iwaha's things. And we talked about this already. Let me just stop.
You have time now. You have time.
I have time?
Yeah.
Okay, then I'll back up
Don't
here.
be pressured.
I'll back up. Okay. Okay, so these are the species that are involved. Big right-handed, small right-handed, big left-handed, small left-handed, monomers, and then there's a total, which is the sum of all these. And notice that this is achiral for the case of sodium chlorate, right? These are left-handed and right-handed. And notice that what we're talking about is not how many crystals, it's how many molecules are in that population. This treatment ignores differences in size distribution between the enantiomeric crystals. It assumes that grinding keeps the distributions sufficiently similar that such differences are secondary. I'll let you think about that just a second. I'm talking too fast. Okay, so I'm not talking about size difference. There's a population of big crystals and a population of small crystals. Big crystals grow, small crystals dissolve, right? And there will be differences because of different size, but they're secondary. Okay? To the extent that they're significant, they would probably reinforce the observed effect by making small crystals from the minor population dissolve faster. To the extent that there's a difference, there probably are smaller for the minor population, and that would reinforce this, but I don't think it's the source of it. Okay, then what processes? There's ablation, knocking pieces off the large crystal. The coalescence, that's the crucial one. Homo coalescence faster than hetero. Dissolution of the small crystals, growth of the large crystals, so communication with solution. And then nucleation of small crystals, which may or may not be relevant. So then these are the differential equations, just for those processes with these materials. And that's the model, except that we're ignoring the nucleation of the small clusters. I doubt that they're relevant. Okay, so in steady state, everything is steady. That's what steady state means. And so there's a trivial solution to these equations, which is that all the solids are zero. Everything is in solution. That's obviously a steady state. So the number of the molecules in monomer are everything. But are there non-trivial solutions? Well, there can be a non-trivial solution when one of the species, right or left-handed, is absent. So it's all one hand. And under those conditions, this is what the concentration of B plus must be at steady state. John tells me that. He's a responsible theoretician, and I have not worked all of this through for myself because it's fairly recent, but I'm pretty sure it's right. The rest of it I've worked through. Now what that means is that this square root, the quantity in the square root must be positive if you're going to have a physical real system, right? Which means, I've done this to prove it for myself. In fact, I did it carefully and noticed that I had a typographical error in my previous version. There's a T that should be here. Okay, so I've corrected that now. In fact, the implementation of the program was correct. John just forgot to put the T in when he wrote this slide. Okay, so G is the rate of growth. Okay, the rate constant for growth, and it has a critical value. And there in principle are two roots here, but only one of them is real because this is the same as this. So this has to be negative. You have to be subtracting something positive in order to have that, to not have the concentration of B plus be negative, which is not very physically realistic. Okay, so there in fact is only one root that will appear. Okay, and then I can show you John's simulation, and it shows some of these features. We won't spend long unless you want to try something with it. Okay, so these are the various rate constants, and notice the ones involving a nucleation are set to 0. Several of them are set to 0 because I don't think they're important. And here, so we start with a little bit more of big ones than small ones, right? Of the green, big, and the red, small, and a certain amount of monomer in solution. And as you numerically integrate it, the red goes away faster than the green and goes to 0. These small crystals rise and get into a steady state. These approach a steady state, and some of the material dissolves. But there I've gone to 500 time intervals, or not 500, 500 units of time. There are many steps in each interval. Now watch what happens if we go to, instead of 500, I'll go to 1500. Go a little bit longer. Takes a minute to integrate. Okay. Nothing exciting, except here. It's not steady anymore. And if I go to 3,000, right? This is the steady state. This was not a steady state. This was I think it must be a saddle point. I'm not quite sure of what its nature is, but at least it's not, this is the steady state. It's the solution to that equation, and it's critical because notice what this happens is the stuff went into solution, but this actually all through here was beginning to grow very slowly as the last remnants of the red went away. Okay? And then it came back out of solution and reached this state. Now, if we had too little material in solution, everything would dissolve. So watch me, I'll lower the amount of monomer. So I'll choose the monomer here at the start, which you see is this number. And I'll lower it to 3 there. Everything dissolved. It's a critical parameter. And everything is critical. I mean, you change anything, it'll do that. The critical value for the rate of absorption is that. Okay. So if you do anything, but it's what you expect. Or if you stir it a little faster. Let's go back to the previous one here. We'll go back. There was a 5 in the last one here, right? So now we have a lot of stuff in the crystal. But let me stir faster. Where's ablation? Here. That may be too little. So I'm stirring a little faster, which makes it dissolve faster. Bingo. Okay, if you want to play any more of those, we can do it. That's the idea.
Thank you, Mike. This reminds me, about just a moment. When I was a student at Harvard, and I had Professor H.C. Brown. The chemists know the big difference between H.C. Brown and Weinstein. And he was asked to give a lecture and come and say, after 15 years that I gave my previous lecture, I was not invited to give another lecture. And then I asked the student, what happened 15 years ago that he was invited and he was not giving the other lecture? Because he presented a lecture which was actually very controversial. And what he had, he came with a gun. And he said, if somebody objects what I'm saying, I'm going to shoot him immediately. Therefore, so my feeling is that here today, what we heard today, Ribo, Wim, Mike, Sabal, Viedma, I think that we don't have a clear picture of what's going on. Everyone looks at the problem from a different angle, and I think this what makes, Axel did excellent, to bring all these people here together, and to be able maybe to come out from here with some kind of a conclusion, whether we can come with a conclusion, what is the real mechanism of this very simple mechanism of grinding the sodium chloride crystals. Okay, now it is open for discussion.
Just a question. Which concentration you must use to have such a
Yeah, well, this is arbitrary because we just put numbers in here. This is not.
Yeah, but
Ribo used some real physical data to try to get this parameter. But anyhow, we just are demonstrating how the equations behave.
It's a general
but the only assumption is that clusters can be selectively incorporated. If you believe that, then this will happen. There may be other things that happen. There may be nucleation, there may be grain boundaries, there may be anything. But this must happen if you can incorporate crystals selectively.
Yeah, but I believe everything, but
I want to sell you something.
yeah, but I just wonder if such a solution must have 1 molar concentration, or maybe 1.5, or maybe 2 molar.
It just depends. It depends on what the solubility of the material
of course.
is. Sodium chloride is very soluble, so
it's why I wonder that such a solution must have at least 3 molar concentration.
could be. Well, what's the solubility of your compound?
It's going to be a very big concentration.
Let's see what the other.
The solvent that we use most of the time, acetonitrile, has a solubility of about 2.6 mass percent.
2.6 mole
Mass.
mass percent. So not very much. A very enormous difference between this system and sodium chloride. Not surprisingly.
I fully agree with you, because I want only to give an explanation of our concept paper. It was from the point of view that it's not possible to get 2 different final states. And we propose the clusters and so on, the same way that you have. And we have looked at in the UABA paper. The UABA paper taking the account these, the sectors. Take into account the clusters and the chiral.
Yeah.
But then, it depends. But you miss somewhere, because you have explained it perfectly how it evolves. But the question is not this. The question is, what occurs when the crystals are exactly the same?
Well, that's a very interesting.
No, that is the question. The question is this.
Well, it's not the question.
Yes,
it's a question. The question I wanted to ask was how it amplifies.
Yes.
Now
You describe
question.
perfectly the evolution. But the question is that in this condition, the racemic state is not stable. What is stable? It is the cryo state.
But stable under grinding.
By grinding. By no grinding is the racemic state.
Yeah.
And that is the UABA paper. What we make is the kinetic analysis. In the kinetical stability analysis, applied to final states and to stationary states, it is the same as the thermodynamic. And that is the question that we say. Because we have supposed that UABA, the people that read the UABA papers, agree with us. But it is, I wonder what is the discussion. And I also agree that the Osborne ripening must not play a role here. It is the important thing is that you have an indirect sulfide recognition between the crystals through the chiral crystal.
That's sufficient, at least. Oswald ripening could play a role, but it's not the crucial role. You need something like this to do it. Oswald ripening absolutely works in one crystal, and it absolutely cannot work for polycrystal.
I explained today that is one crystal is not stable, but also many crystals. When you take into account the sulfides, then it is indicates that the orbital crystal, the three-nanometer crystal, are more stable than the racemic. Of course,
This is what Raphael talked about this morning.
Okay. Could we look again at the equations with this B and S plus and minus, please?
Yeah.
What I would like to know is what corresponds to the racemization parameter of Wim's. Wim had this racemization parameter, which was, of course, the crucial parameter. What?
I think they are the same.
Yeah, but what was it again? I just want to see that in the equation.
This particular simulation is for sodium chlorate.
Yes.
So there is no racemization step.
Really?
It's a common solvent. We could write it we could do an Excel program for 2 pools that can interconvert at a certain rate, but we haven't done it. This is only for the simulation we've done, and the equations are for achiral in solution. It wouldn't be much work to change it, to make it have different.
So you're saying
there's a single.
So you're saying there's no interaction between the 2 poles, left and right? I thought there was.
This this is the model I've shown you, is for in solution it's achiral.
Yeah.
In Vim's case, the solution is chiral, and you have two of these.
Okay, I see.
Right, and then you have a rate between them. But if you have only one, there's no rate.
Is that true?
I think that during the growth, that the conversion in the solution is rate determined. All the solid needs to pass the DBU to get on the other crystal.
Yeah.
And this is the step. And I think that we didn't incorporate the solution in our model because lots of complex things can go on. I mean, we're discussing it all the time now. Therefore, we kept it as simple as possible. And we did mention the Gauss clusters, for instance, for the sodium chloride case. I think it is the same. And what you observe here is that you see a sort of, once you enter the single Gauss solid state at the end, you will see that the concentration drops, isn't it? Yeah,
sure.
That's the same in our model as that we get.
And the reason is, in my model, the reason the concentration drops is at the end there are more crystals, so more ways of reincorporating, so slower dissolution.
Yeah. Well,
so more the crystals accumulate if they dissolve slower.
The way we see that in our model is the last picture I showed you. You see that we are forming larger crystals, and larger crystals correspond to a lower concentration in the solution. So
but you don't. That's Ostwald ripening, as you say. But you don't need that. If you have more crystals of the same size, you also get the effect because there are more ways of trapping the clusters. The more crystals you have of a given kind, the more you can trap the clusters. The more you trap the clusters, the less they dissolve. The less they dissolve, the more solid there is.
Yeah, I agree with this.
Yeah.
Absolutely. The only thing is that what we call Ostwald ripening is this going on process of dissolution of small clusters and growing of larger ones.
Yeah.
And that's, I interpret this as Ostwald ripening because it's the difference between the two.
You know, the reason Ostwald was interested in Ostwald ripening, he wrote a textbook this big about analytical chemistry. And the practical application, as you know, of Ostwald ripening is to make crystals bigger so you can filter them more efficiently, right? Yeah. While you're grinding in a steady state, the crystals aren't getting bigger, I think. Maybe they might get marginally bigger, but I can't believe that you don't reach I can't believe you go all the way to a single crystal with grinding.
Okay, then I think we're talking about the same thing. We are talking about...
No, there's a feature of Ostwald ripening that does not occur here. And that is that the crystals get steadily bigger and bigger. And the reason is the small crystals dissolve, the large crystals grow. And people often talk about a solution being supersaturated or undersaturated. But that's always a relative term. Compared to what? Compared to crystals of what size? So the in steady state, the smallest crystals are always dissolving, and the largest crystals are always growing. But as the smaller crystals go away, the concentration in solution slowly drops. So that bigger and bigger crystals become stable, and bigger crystals become unstable. You keep raising the ceiling or the floor, right? And that's what I think of as Ostwald ripening, the steady growth in size. But this does not require a steady growth in size. If after grinding for 3 weeks, the size of the crystal stops changing, this mechanism still works. But, I mean, in a sense, Ostwald ripening is the same because it talks about subcritical and supercritical. To the extent that that's what you mean when you say Ostwald ripening, I agree. But if you require the crystals to keep getting bigger, as they do in real Ostwald ripening, traditional Ostwald ripening, then I think that's not required in this case.
That's why we call it attrition enhanced, because you need the attrition to see this effect.
Yeah, you have attrition enhanced dissolution, which is retarded by absorption.
Yeah, so I think
and the more absorption, the slower dissolution, net dissolution.
Yes, something is missing in the discussion of the day. That is, by milling, you arrive to a constant size of the crystal.
That's what I think.
It is impossible then to apply the also written in this question, because when one grows too much, it is also green. And then this explanation will represent that you have chirality, the enantiomeric excess increase. And then when you mill more time, you go to racemization. And then there will be a point that you have chirality, and then it disappears to racemization. But it don't disappear. It means that the stable state is the cradle.
Yeah, it's because it's not that you do it for a longer time, but that you do it harder. Yes.
No.
More, no.
Well, it is the experiment is very hard. And you have a constant size. And when a crystal, grows, this will be with more probability triturate. It means that you will have a stationary state also in the beginning, and you have it sure. And that it cannot explain this one, because in this case, at the beginning of the gradient, you will have chirality, and then it will be this, the time disappears to the racemic state. But
I don't see how that happens in this system.
system.
You would go, in my system, as I understand it, if you grind too rapidly, do too much ablation, then everything dissolves. That destroys chirality, but in a sort of trivial way.
It depends on the solubility.
Well, but you increase the solubility by grinding harder.
Yes, I agree, because this is perfect to explain, but I repeat, if the racemic state is the most stable or not.
But under grinding.
Under grinding.
Yeah.
Well, the stability depends of the connection, of the reaction path that connect the species. And of course, there are some connections, but that disappears in time. And the final state is different.
But I think that these steady states, or the final states that I find within our model, those are the final state. They're not going to suddenly change.
No.
You mean you do not agree?
It will not disappear. It will remain in the chaos.
Yeah. Okay. Good.
Because when you stop the mill, the grounding.
Oh, when you stop.
And what occurs? Racemicide? No.
Well, no. Then it'll lost all grinding. You stop grinding.
And it will remain in the same state.
Well, it's still dissolving and depositing. That will lead to oswald ripening.
But then enantiomeric excess will not change.
Oh, but it will go all to one. In the fullness of time, after you and I are long gone.
Well, I want to return back to this question. If I understood correctly your model, you're saying is that everything depends on the recognition of the crystals or the clusters of the given entity.
That's what the law means by chiral.
Yeah, this is the key point.
It is the key point.
Now, the question is, if you go to the physical situation, for a cluster to be attached to a crystal, it has to remove the molecules from the surface in order to be attached.
Yeah, I know.
And I think that in our case, when we have studied solvent effect on crystal growth in many systems, we have shown that the stripping of the solvent molecules from the surface is the redetermining step.
But you know,
just a moment, Mike. So I want to ask a simple experiment, really. If you check the solvent, because if you check some solvent which is less attached to the surface, and the energy of stripping of that solvent from the surface is much lower, smaller as compared to the other solvent, and then naturally what's maybe your mechanism, then maybe the redetermining step will be the attachment of the cluster to the surface, whereas in the other one maybe that in different solvent where you have very strong interactions with the surface, then you go that then you have a different mechanism.
Yeah, but the idea of a rate determining step is a simplification to make things easy to understand and deal with. Always, if you look close enough, there's a little bit of something that might do that. And all you need for this mechanism is that a cluster is a little better. And in Vin's case, there's no question that one cluster is going to be better than the other. when you have to epimerize them, all right?
Yeah, but if you have the sodium chloride case, which is an ionic crystal, which attach water very strongly by electrostatic interaction, and then moving the water molecules from that surface, like in the polar crystal, which grow unidirectionally. And the reason why they grow unidirectionally is because to strip the water from one end, from one pole, is much more easy than the other.
Josh Baraban has some other ideas about that.
Okay, Henry.
Is it possible to have some information by looking to the fractal dimension?
In this case?
No, in sodium chloride.
In sodium.
Because you said
What?
the surface could be smooth. Or could be,
That's not the I'm not a mathematician. They call this fractal. The idea is you look at all distances. There are many pairs of crystals. You have n crystals there, n times n minus 1 pairs or something like that. And you look at all these pair distances. Okay? So you make a table of all the distances between pairs, and many of these. And you see how they are distributed. How many are at this distance, how many are at this distance, how many are at this distance. If things are random, if you just drop things at random, then it just has to do with the area, and it will scale with the square of the distance. But if they're correlated, they group for small distances. So you have a different power law for how these numbers are distributed. And that's what we observed in sodium chlorate, that the power law is not second power.
Okay.
Only one thing more. There is many models in science.
I told you what happened with models. There's a joke. Professor Prelog, the famous Professor Prelog, was in a Bergenstadt conference, and there was a young person there playing with models. And then he said, "Young men, be aware playing with models. See what happened to Porfimo. Porfimo was the Minister of Defense of England. See when he was playing with models, what happened to him." Be careful.
Okay. We can discuss about this model. But we can do prediction, experiments that valid the model, one model or the other one. I have a model, and I have a prediction, and I am working in this prediction. I am working in equilibrium. There is no cluster. Your model, all the models have cluster, chiral cluster. Well, my experiment have no cluster. I say, if my experiment works, and I am able to achieve total chiral purity from amino acid in equilibrium, this is correct in your model.
Well, even models can be very good at suggesting experiments, right? But it's very difficult to decide. What Newton and Bacon first, Francis Bacon, in the 17th century or the early 17th century, Bacon talked about the experimentum crucis, which is a road is going along, and the road bifurcates, and there's a cross at the road that says "Go this way." That's the experimentum crucis, and that's what the people in that period, the scientists, early Royal Society scientists, looked for, was something that would absolutely decide between this path and this path. Okay, but there are not so many models. There are not so many cases where, when you look at it really carefully, like Newton thought he had the experimentum crucis for light, whether it was pulses or substance. But it turns out it's both. So it was if you formulate the question a certain way, then you may think you have an experimentum crucis. But you do the experiment, and the experiment has its value forever. But that doesn't necessarily prove a particular mechanism. It just discriminates maybe between two mechanisms until someone thinks hard enough to see why it didn't.
But in science,
That was true for
science is a model, a theory, a hypothesis, explain many different things is better than the other one that only explain one or two. It is a science. then if I perform this experiment, then perhaps my model and the model of Nurduil is that have no chiral cluster is perhaps more available, more correct. Do you agree?
I think in order to evaluate it, I would have to see what the predictions are and what the experiment is.
But I think, Cristobal, and not in the case of grinding, we have done studies with tailor-made auxiliaries in the nucleation crystallization of conglomerates.
Yes.
And in all this experiment, we have to invoke the formation of chiral clusters in solution.
In the Nurduil experiment.
No, and also in the case of controlling crystal polymorphism, we additive with auxiliary molecules. Actually, we have always to assume the formation, the presence of clusters in solution.
Yes,
Therefore, I think this point, people that are working on crystal growth, I think are assuming now I think they accept this idea that a crystal can cross a critical site by interaction of certain clusters which can interact with one another to form a large cluster which can cross the critical site and to form the crystal. So this point seems to me that is quite, this assumption seems to me quite reasonable.
Yes,
that you must have some kind of
cluster. But it's more
cluster.
difficult to have chiral clusters in equilibrium. It's more difficult.
In what?
It's more difficult to have chiral clusters in equilibrium. It's more difficult.
In equilibrium?
I think so. Yes.
Yeah, in equilibrium, no. Well, but chiral clusters would exist in equilibrium, but in very small amount and reversibly by microscopic reversibility. So they're not going to do the job under those. It's when they're it's abrasion.
I agree with you.
Okay, I think that, it was a very good day, and I started with telling you a small secret. And I will terminate then by telling you another secret that I learned 2 days ago, and I remember this a number of years ago. Today is the birthday of Professor McBride. He found that. I received the email.
I assume you're clapping for my mother.
I received the email, not only you received the email, I received an email the other day when I'm trying to look on my computer. I say, this is not for you. From Clarence McBride, his wife, and she asked me that I should congratulate you, not only in our name, but she sends you all her warmth and love for this day.
Oh,
and I think that really this is a great day. What I can wish you is that in the next years you will have such an opportunity like today to be able to speak with such an enthusiasm. Although, things that people accept or disaccept, it's very, very exciting, and to continue many additional years of that kind of excitement.
Thank you very much, Mayor. Thank you.